Now let's look at temporary overvoltage, TOV, defined as phase to ground or phase-to-phase oscillating overvoltages. They are normally of relatively long duration. Their patterns are undamped or weakly damped at a given location, in contrast to switching and lightning overvoltages, which are highly damped and of short duration. Based on the frequency of oscillation, they can be classified into three groups. So if we can go back to here, so you can see that the temporary overvoltages are usually in oscillation, right? It's not damped, right? In switching and lightning, it is damped, right? High frequency and damped, but for temporary overvoltages, it's usually in oscillation, appear in seconds, alright? Relatively long duration compared to lightning and switching. So you can classify into three groups: type A, type B, and type C TOV. Type A TOV, overvoltages having oscillation frequency at or close to the power frequency. At or close to the power frequency, or 50 or 60 Hz, depends on where you are located, with pure or nearly pure sinusoidal waveform. Can be either steady or quasi-steady, can be caused by various problems and faults. Examples are load rejection, asymmetric short circuit, capacitance effect on open lines, and resonance in linear circuits produced by open conductor. Alright, type B TOV, overvoltages having oscillation frequencies higher than the power frequency. They are due to higher, even, or odd harmonics. Alright, usually because of harmonics. Because of the harmonics, then frequency is higher than the power frequency. May be formed by a steady state resonance or ferroresonance phenomena in the system. And then type C, overvoltages, temporary overvoltages, is for frequencies lower than the power frequency. So we have three types: A, B, C. A is when the overvoltages appear near to the power frequency, 50 Hz or 60 Hz. Type B is when the oscillation overvoltages appear frequency higher than the power frequency, and type C is when the overvoltages oscillation appear at frequencies lower than 50 Hz or 60 Hz. They are due to forced subharmonic oscillation. For example, they can occur in a power transformer. They can occur if a power transformer remains connected to a source with a large capacitance after a fault condition or switching operations. So basically, based on the type of the temporary overvoltages, you can actually determine the possible cause of these overvoltages. TOV is classified as internal overvoltages, so basically due to the system and its parameter, okay, appear internally. Some types are associated with the same faults that can generate switching overvoltages as well. Alright, so when the switching overvoltages, it will not just appear switching. Example, if we have this kind of phenomena in the system, it will not just cause switching overvoltages, but it is also cause temporary overvoltages as well. Alright, so generally a voltage rise up to 1.2 pu can occur during load rejection or non-compensated transmission lines due to Ferranti effect at the substation end of the line that is disconnected from the source. Right? Ferranti effect: the voltage increase on a long line due to the current flow through the shunt capacitance, which produce a voltage across the source and line conductors. Okay, so what is Ferranti effect? This is it. and cause temporary overvoltages in the system. So due to resonance and ferrous condition, example, when large capacitive elements and inductive elements having non-linear magnetizing characteristic are energized or through sudden load changes. Alright, so these are examples of temporary overvoltages, phenomena that can cause temporary overvoltages. The voltage rise caused by these problems is generally between 1.4 and 1.5 per unit of the system voltage. Also, TOV can be generated by earth fault on the line. So you can see here when there's several phenomena appear in the system due to faults, due to changes of the system in the system. Not just cause switching over voltage, it can also cause temporary over voltages, right? So when there's earth faults on the line, which can cause a rise in voltages up to 1.4 pu for earth neutral system and square root of 3 per unit on non-earth system. Alright, the duration of the TOV is determined by the time taken to restore the system of fault clearing. Okay, really depends on how long the process to complete. Okay, if the process to clear the faults takes a long time, then the TOV will appear a long time in the system. Okay, generally less than 1 second in the first case and less than 10 seconds in the second case. It depends on how quick we can clear the system. TOV have no significant influence on overhead line design, as only short air gap clearance are needed to prevent flashover. So when designing overhead line, we are more concerned on the lightning overvoltages, not on TOV. The overvoltage amplitudes are normally less severe and can normally be cleared in times significantly less than 1 second. Okay. Furthermore, extra high voltage system networks are generally equipped with shunt reactors, series capacitors, and static compensators to limit the voltage rise from sudden changes of load. So we have these reactors, capacitors, compensators to control the system voltage, to avoid it from go beyond the rated voltage. Voltage rise caused by resonance and ferroresonance problems can be limited by detuning the system from the resonant frequency, by changing the system configuration, or by changing damping resistance. So these are actually can be fixed. In some cases, such arresters may be employed to limit temporary overvoltage due to resonance effect. Right? Usually use such arrestor to arrest the surge, okay, to reduce the lightning overvoltages in the system. However, we can also use this arrestor to limit the TOV due to resonance effect. And then finally, the last one, very fast frequency overvoltages. Very fast front overvoltages appear less than 100 nanoseconds. Okay, less than 0.1 microsecond. So this is, if you can see, it is under this category, VFFO, very fast front overvoltages, PU up to 2.5. Alright, so VFFO, very fast front overvoltages, typically occur within gas insulated substation GIS. Okay, due to the switching operations of the disconnector switch or of the SF6 circuit breaker. So of course, as we discussed before, switching on and off of the breaker can cause switching over voltages. However, if the switching happens in gas insulated substation, this will cause different type of overvoltages, which is very fast front overvoltages. Okay, happens in less than 100 nanosecond. The restrikes or pre-strikes occurring during the switching operations of opening and closing will generate overvoltages that can propagate within the GIS or beyond. Um, so the switching operation or the breaker in the gas insulated switchgear or gas insulated substation will cause this kind of overvoltages, and will not just happen in the substation, but it can also travel beyond the GIS. VFFO are superimposed on the system voltage with a magnitude that can reach 2 per unit. Okay, do not have the waveform here, but you can just simply imagine that this is the system voltage, all right, and then the VFFO appear very short time, less than 100 nanosecond, but it can reach up to 2 per unit, 2.5 per unit, up to 1 per unit. Sorry, this TOV can reach 2 per unit or even up to 2.5 per unit. So VFFO not normally considered in overhead line design. Okay, it's not a concern in overhead line. However, it may be important in circuit breaker design, gas insulated switchgear design. So less research activity has been published about the VFFO. So you can see here, this is actually related to the whole overvoltages, alright, power system control and dynamics or electromechanical phenomena, basically such as fault clearing, and then the control of the temporary overvoltages. So this appear in seconds or even up to minutes, depends on how fast we clear the fault. But for overvoltages appear in millisecond and microsecond. This is basically overvoltages with transient shape of transient and surges because of electromagnetic phenomena due to lightning, usually mainly due to lightning, for example. And then here we have power frequency. If you can recall, temporary overvoltages type A appear here, temporary overvoltages type B, which appear at slightly higher frequency. So it can appear here, temporary overvoltages type C at low frequency than the power frequency, less than 50 Hz or 60 Hz appear here, right?